Good afternoon, everybody. Welcome to Tibbetts Physics. What is crappin'? Today, it's a little bit of a history lesson. We'll be looking at Galileo and inertia and his contributions. So a little bit about Galileo. One thing that he questioned in the early 1600s was what causes things to move. We'll call it objects. So imagine you're sitting on a football field and you see a dollar bill sitting there alongside you, and you go up to grab it, and all of a sudden the dollar bill moves away a little bit. So here you are, you got a dollar bill, and we'll call it a $100 bill. And you go up to grab it, so you walk over and you go up to grab it, and all of a sudden the $100 bill, moves backwards. You're going to ask yourself, what the heck caused this to move backwards? Prior to asking yourself, you're probably going to go up and try and grab it again, and notice that something is pulling it backwards. So hopefully you end up figuring out that the $100 bill is attached to a string, and there's someone that's applying a force to pull the $100 bill, backwards. So Galileo questioned, what is it that causes objects to move? And he made a few contributions towards answering this question. His first contribution was, let's say that we were standing on a building and you dropped a ball outside of this building on the top. Prior to Galileo, one would think that the ball, let's see, we've got the Earth here, and the Earth is rotating on its axis. So prior to Galileo, one would think that the ball would also follow a curved path. It would kind of go backwards and run into the wall, since everything else is moving forwards. That doesn't make sense to us nowadays. It's common sense that the ball, while the Earth is rotating, the ball is also rotating at the same speed as Earth. So if you drop the ball is just going to fall straight down. And even though it's moving along Earth's rotation, it's moving relative to Earth's rotation as well as you. So his first contribution was, if you dropped an object off a building, B-U-I-L-D, it falls straight down because it is moving relative to the Earth. Again, common sense to us nowadays, but believe it or not, people actually did not test this experiment out. They just discussed it, and it wasn't until Galileo actually attempted this by dropping a ball or something off the Leaning Tower of Pisa that he discovered that the ball fell straight down and didn't go crashing into the tower. So that's his first contribution. Now, his second contribution is a little bit more trickier. Let's say that Galileo bought an orange at a grocery store. Let me use orange for orange. And this happened to be a bad orange, but Galileo knew going into shopping that buying fruits and vegetables is a gamble. So if you get a bad one, it's your own fault. Unfortunately, you can't return fruits and vegetables to the grocery store unless you know Kramer's supermarket guy that could hook you up. So anyways, he's going to roll this orange across the floor. Prior to Galileo, people assumed, or people thought, that in order for this orange to keep on going across the floor, that someone must be continuously applying a force to it. So you have to keep on pushing it to keep it moving, otherwise it'll stop. But that's backwards thinking. This ball, once it's pushed forwards, the orange, once it's pushed forwards, it wants to keep on moving. But there's something that causes it to stop, and that's a backwards force that we experience every day, and that's friction. So second contribution is kind of the opposite of we think on an everyday life. So he said that no force is required to keep an object in motion. Rather, it's the opposite. A force is required to slow an object down, slow or stop. So we naturally think that a force is required because friction we experience every day, but if we move that force of friction, then that object would move on forever until something came out and stopped it. Galileo went on to define friction, and it's the opposing force, the force that opposes motion the direction of motion and is parallel to the surface. We'll define friction in more details when we actually talk about the coefficient of friction. And in class, we'll actually look at Galileo's experiments to test his second contribution as to whether or not a force is required to keep an object moving, or if a force is required to keep an object, or if a force is required to slow an object down, which was the case. So he ended up saying, he summarized his results. That's a bad underline. Summary of experiments. So he said the tendency of a moving body to keep moving is its natural state. And that every object resists change to its current state of motion. So one more time, the tendency of a moving object to keep moving is its natural state, and that every object resists change to its current state of motion. In other words, if an object wants to keep on, or if an object is moving, it wants to keep on moving, and if an object is at rest, it wants to remain at rest. Not rushed. We call this inertia. The inertia is the property of an object to resist changes of its current state, of motion. In other words, the more massive an object is, the more likely it is to stay in its current state of motion. It's going to take more force to change it. The less massive, it's going to take less force to change it. So we could say that inertia is mass. And one quick addition, friction is abbreviated as F sub F. F sub F. Unfortunately, in 1642, Galileo died. All of us have to die at some point, so it just happened to be in 1642. Fortunately, on 1642, on Christmas Day, depending on whose calendar you're looking at, a very famous scientist was born that helped explain all the physics we know today. Well, the majority of physics we know today. And we'll learn that next time. See ya.